Probability and statistics, the hypergeometric distribution. Let's look at the preceding section first, the binomial distribution. This was on the previous video, and let's do a comparison. First of all, the binomial distribution is used when each event in the process results in one of two possible outcomes, success or failure, head or tail, wrong or right, correct or incorrect in a multiple choice, defective or not in quality control, bullseye or not when a marksman is shooting for a target. The probability of success must be the same for each event. So, half head, half tail, or half head, half not tail. Quarter correct, 3/4 incorrect. This is based on previous performance, not continuous, based on the results over a given time period. So perhaps in the previous month there were found to be 50 defective products out of 1,000, so therefore 50 over 1,000 gives us our probability of defective. Maybe the marksman over the last month has hit 400 bullseyes in 1,000 shots. That will give us our probability of hitting the bullseye. The events are independent, meaning here that a success in one event does not influence the probability of success in another. Of course, this one is fine if it's based on a latent defect in raw materials or machinery. In other words, the machinery is causing the problem or the materials. But if it's human beings causing the material, they could improve and the probability will change. So we are basing this binomial distribution on the fact that nothing changes. Same here, a marksman every time he or she shoots, whether missing or hitting, could learn something and change the probability. So we're disregarding the effects of learning or practice in the short term. Let's have a look at the hypergeometric distribution. We use it when the population from which the selection is made consists of two or more types of object, red cards or black cards, male or females in a committee. The sample is chosen without replacement, so when you deal out cards to somebody, then you don't replace the card, so the probabilities change. Selection automatically removes the person from the group, so probabilities change. Events are dependent, meaning that the probability changes with each selection. In other words, here, for each card dealt, fewer left of that color, suit, number, whatever you're looking at, and there are also fewer cards to deal from, so the probability changes. Deal out a king, there are only 3 kings left, there are only 51 cards left, so chance of another king is 3 over 51. Chances of anything else is over 51. Here too, once you've chosen a male or a female, there will be fewer males or females, depending on what was chosen, from that person's group, and there will also be fewer to choose from overall. Let's look at an example. Choosing from the alphabet, I'm choosing 5 letters without repetition. Find the probability that 2 of the letters chosen are vowels. Well, it's 2 types of object, vowels and consonant. Notice it's not success or failure, it's 2 objects. So we could have more than 2 objects. It doesn't matter. We could have 10 objects in the hypergeometric. You'll see the way it is done. No replacement. Well, the word without repetition says no replacement. It's no repetition. Probability changes. It does because of the no repetition. Therefore, hypergeometric and not binomial. So, number of ways to choose 2 vowels. We're choosing 2 from 5. Order doesn't matter, so it's a combination. Choosing 3 consonants from the remaining 21 letters. Once again, it doesn't matter in order, whether you choose an H, G, then K, or G, H, and then K. It doesn't matter. You've chosen 3 consonants. So it's a combination. No order comes into the equation. Number of ways of choosing both, we're going to take them, and by the counting principle, if that's the number of ways for that, and this is the number of ways for this, we multiply them to get the number of ways for the whole lot. Total number of ways of choosing 5 letters, well, there are 26 letters in the alphabet, and we're choosing 5. So now what we're going to do is we're going to put this value, number of ways of choosing that, over the total. And that gives us 0.202. So let's have a look at another one. A bag contains 8 red balls, 4 black balls, 3 yellow balls. 4 balls are taken at random without replacement from the bag. Determine the probability distribution of the number of yellow balls taken and draw a histogram illustrating this distribution. So this is going to be, in this case, yellow balls or not yellow balls. So it's going to be 3 versus 12 and a total of 15. Number of ways to choose yellow. Well, it's going to be number of ways of selecting yellow. Notice selection, not arrange, n from 3. Number of selecting the non-yellow, 4 minus n from 12. There are 4 balls we're choosing, so if we choose n yellow, we've got 4 minus n of the others, and there are 3 yellow and there are 12 other balls. Total number of selections, 4 from 15. So now what we have to do is we're going to have to do a mutually exclusive calculation. We're going to have to work out number of no yellow, then 1 yellow, 2 yellow, 3 yellow. Right, so no yellows. Here we are. Combination of 0 from 3, and we're going to find 4 from 12, and it's 4 from 15. 1 yellow. 2 yellows. Notice once again, combination of 2 from 3 yellows, 2 from 12 are the remaining, because we're choosing 4 balls, and 4 from 15 is the total number. And 3 yellow by the same combinations. So there is the probability distribution. There are the probabilities of the various quantities of yellow balls. Histogram, here we go. And note that it is not symmetrical, affected by the changing probabilities, the dependence. So we have a formula. Looks terrible, but not really. There we are. There's what we need. I'll relate these with the next example. Okay, so here we are. 5 cards are drawn without replacement from a deck of 52 cards. What's the probability of exactly 3 kings drawn? Now we're going to do the same as we did with the balls earlier. We're going to find the number of ways in which 3 kings can be drawn, the number of ways in which the other 2 cards can be drawn, and divide by the total number of ways. We're going to have to do it by mutually exclusive again, because if we want 3 kings, we'll have to work out the probability of 1, 2, or 3 kings, or no kings. N is 52. So the n, total number of items. K, number of the required item. Well, the required item is kings, and there are 4 of them. N, the size of the sample. Well, the sample is what we're drawing, and we're drawing 5, so N is 5. X, the required number of the required item. Well, we're requiring kings, and we require 3 of them, so X is 3. So we're now calculating exactly 3 kings, so we don't have to worry about mutually exclusive or anything. So probability X equals 3. We can apply the formula, or we can just do it by common sense, but there is the formula applying these values. Number of ways of choosing a 3 from 4 selection, number of ways of choosing 2 from 48. Here we are, 3 from 4 and 2 from 48, and there's the total number, giving us 0.0017, and that is the probability of drawing exactly 3 kings. For those of you who are poker players, there's not a big chance of drawing 3 kings, but I suppose you can multiply that by 13 to find your probability of drawing a trip